Today I would like to talk to you about the general characteristics of group 15 elements. My dear students, I am Dr. Digna Varghese. Contents of the presentation: nitrogen family, electronic configuration, size, ionization energy, electronegativity, oxidation state, atomicity, allotropy. Nitrogen family. The group is also known as nitrogen, is any of the chemical elements in group 15 of the periodic table. Nitrogens are nitrogen, phosphorus, arsenic, antimony, bismuth, and MOSCOVIUM. A nitrogen is a term derived from the ancient Greek word nigen to meaning to choke. This refers to the choking property of the nitrogen gas. They have also been called the pentals. They are characteristics of having 5 valence electrons. That is, their outer electronic configuration for the group 15 members is NH2 NP3. MOSCOVIUM is a synthetic element. Nitrogen makes up 25 parts per million of the earth crust, 5 parts per million of the soil on average, 100 to 500 parts per trillion of seawater, and 78% of dry air. The majority of nitrogen on earth is in the form of nitrogen gas, but some nitrate minerals do exist. Phosphorus makes up 0.1% of the earth's crust, making it the 11th most abundant element there. Arsenic makes 1.5 parts per million of the earth crust, making it the 53rd most abundant element there. Antimony makes up 0.2 parts per million of the earth's crust, making it the 63rd most abundant element there. Bismuth makes 48 parts per million billion of the earth's crust, making it the 70th most abundant element there, and MOSCOVIUM is produced several atoms at a time in particle accelerators. Nitrogen, the first member of nitrogen family or group 15 elements or nitrogens. We know the symbol of nitrogen is N, and its atomic number is 7, and its mass number is 14. Nitrogen is the most common pure element in the earth, making up 78.1% of the entire volume of the atmosphere. Nitrogen was discovered and isolated by the Scottish physician Daniel Rutherford in 1772. Nitrogen is a non-metallic element. It has no color, taste, or odor. It is a non-combustible gas. Important nitrogen containing minerals are nitre, that is potassium nitrate, and soda nitrate, that is sodium nitrate, which are found in desert regions and are important components of fertilizers. Nitrogen has very little solubility in liquids. Nitrogen can be produced by fractional distillation of air. Nitrogen has two stable isotopes, 7N14 and 7N15. Phosphorus, the second element of the group 15. We know the symbol of the phosphorus is P, its atomic number is 15, mass number is 30.974. Elemental phosphorus exists in two major forms, white phosphorus and red phosphorus, but because it is highly reactive, phosphorus is never found as a free element on Earth. White phosphorus emits a faint glow when exposed to oxygen, taken from Greek mythology, meaning light bearer. Latin word, it is come from the Latin word Lucifer, referring to the morning star, the planet Venus. The glow of phosphorus is caused by the oxidation of white phosphorus, not red phosphorus, a process now called chemiluminescence. Chemiluminescence, also known as chemoluminescence, is the emission of light, that is luminescence, as a result of chemical reaction. Here we can see in a conical flask the chemiluminescence, that is the emission of light by the use of a chemical or as a result of chemical reaction. 23 isotopes of phosphorus are known, ranging from phosphorus 25 to phosphorus 47. Only phosphorus 31 is stable, that is the elemental phosphorus existing the with a mass number 31, that is 30.974 actually, which is stable and is therefore present at 100% abundance. The term phosphorescence, meaning glow after illumination, derives from the property of phosphorus. Okay, the important property like phosphorescence, that is the term derived from the element phosphorus. Although the word has since been used for a different physical process that produces a glow. The discovery of phosphorus is credited to the German alchemist Henning Brandt in 1669. Henning Brandt was a German merchant. He was a pharmacist. He was an alchemist too. Brandt experimented with the urine. Henning Brandt experimented with urine, which contained considerable quantities of dissolved phosphates from normal metabolism. Robert Boyle published the method of manufacturing phosphorus. Robert Boyle was an Anglo-Irish natural philosopher, chemist, physicist, and inventor. Phosphorus was the 13th element to be discovered because of its tendency to spontaneously combust when left alone in air. It is sometimes referred to as the devil's element. In 1769, Johann Gottlieb Gahn and Carl Wilhelm Scheele showed that calcium phosphate is found in bones, and they obtained elemental phosphorus from bone ash. Next element is arsenic. We know the symbol of arsenic is As. Its atomic number is 33. Mass number is 74.921. Arsenic is a metalloid that can exhibit both the properties of a nonmetal and a metal, or a properties that show in between the metallic character and that of the non-metallic character. The word arsenic has its origin in the Syriac word sarnica, meaning yellow, literally gold colored, and hence yellow opiment. One of the mineral of arsenic is opiment, As2S3. Arsenic occurs in nature as a monoisotopic element composed of stable isotope arsenic 75, that is its actually mass number, that is 74.921. 33 radioisotopes have also been synthesized. Only one natural isotope, that is the actual arsenic element, but there is 33 radioisotopes have been synthesized, ranging in atomic mass from 60 to 92. The most stable of these is 73 arsenic with a half-life of 80.3 days. All other isotopes have half-lives of under 1 day. Antimony. Antimony, the symbol is Sb. and its atomic number is 51, mass number is 121.76. Antimony is a silvery, lustrous, gray metalloid. It is found in nature mainly as the sulfide mineral stibnite, that is having the formula Sb2S3. Antimony has two stable isotopes, antimony 121 with a natural abundance of 57.36 and antimony 123 with a natural abundance of 42.64. It also has 35 radioisotopes. Antimony 3 sulfide is used in the heads of some safety matches, that is in the matchbox, head of the matchbox. Bismuth. We know the symbol is Bi, atomic number is 83, mass number is 208.98040. Bismuth is a brittle crystalline white metal with a slight pink tinge. It has a variety of uses including cosmetics, alloys, fire extinguishers and ammunition. It is probably best known as the main ingredient in stomachache remedies such as Pepto-Bismol. Bismuth element on the periodic table of elements is a post-transition metal according to Los Alamos National Laboratory. The only primordial isotope of bismuth is bismuth 209, that is the one was traditionally regarded as the heaviest stable isotope of bismuth. Synthetic bismuth crystal exhibiting the stair-step crystal structure and iridescence color, which are produced by interference of light within the oxide film on its surface. Iridescence, also known as goniochromism, is the phenomenon of certain surfaces that appear to gradually change color as the angle of view or the angle of illumination changes. Moscovium. We know this is the synthetic element, only synthetic element present in the nitrogen family. Moscovium is a synthetic chemical element with a simple Mc and the atomic number is 115 and its mass number is 288. Moscovium is sometimes known as Eka bismuth, which is an alternative name for ununpentinium. It was first synthesized in 2003 by a joint team of Russian and American scientists at the Joint Institute for Nuclear Research (JNR) in Dubna, Russia. Headed by Russian nuclear physicist Yuri Gagarin, the team included American scientists of the Lawrence Livermore National Laboratory. The researchers on February 2, 2004 stated in Physical Review C that they bombarded americium-243 with calcium-48 ions to produce 4 atoms of moscovium. When americium-243 bombarded with the calcium-48 ions to produce moscovium-288, which undergo a radioactive decay emission of alpha particles to nihonium in about 100 milliseconds. By the alpha decay, the element atomic number decreases by 2 units and the mass number decreased by 4 units. Sources. The main source of nitrogen include atmospheric precipitation, geological sources, agricultural land, livestock and poultry operations, and urban waste. Agricultural emissions show a strong increase due to the application of fertilizer to agricultural soils, grazing of animals, and spreading of animal manure. Nitrogen gas is an industrial gas produced by the fractional distillation of liquid air or by mechanical means using gaseous air. Most inorganic phosphates used for this purpose are derived from natural rock phosphates, principally found in Africa, Northern Europe, Asia, the Middle East, and the USA. However, in the natural form, these are unsuitable for direct use in animal feed because the phosphorus they contain cannot be metabolized by animals. The method for obtaining phosphorus is from calcium phosphate. Be heated to 1200 to 1500 degrees Celsius with sand, which is mostly silicon dioxide, and coke to produce vaporized P4. That is, when calcium phosphate reacts with the sand and carbon to produce vaporized phosphorus. Fish, shellfish, meat, poultry, dairy products, and cereals can also be dietary product sources of arsenic, although the exposure from these foods is generally much lower compared to the exposure through contaminated groundwater. In seafood, arsenic is mainly found in its less toxic organic form. Naturally occurring sources of human exposure include volcanic ash, weathering of minerals and ores, and mineralized groundwater. Antimony and its compounds are naturally present in the Earth's crust and are released into the environment by natural discharges such as wind-blown dust, volcanic eruptions, sea spray, forest fires, and biogenic source. Antimony can be isolated from the crude antimony sulfide by reduction with a scrap ion, giving antimony. Bismuth occurs as the native metal and in the ores such as bismuthnite and bismite. The major commercial source of bismuth is a byproduct of refining lead, copper, tin, silver, and gold ores. To make the MOSCOVIUM, the scientists in Russia and the United States of America bombarded atoms of americium with ions of calcium in a cyclotron. Uses of nitrogen family members. The first element is nitrogen. Two of the elements in the nitrogen family, that is nitrogen and phosphorus, are essential for life. Phosphorus is used in matches, fireworks, and fertilizers. It's also used to make phosphoric acid. Likewise, nitrogen is also used for so many chemicals, nitric acid, etc. But we are all heard about nowadays as a Lebanon explosion. It was a humanitarian explosion that is based on the ammonium nitrate that is kept or stored in a room in a bulk amount. When ammonium nitrate is reacts with any combustible material, that will be exploded. In Lebanon, it's so many humans or people affected by these explosions, and so many death happens there. Ammonium nitrate is mainly used for fertilizing. In our lab, it is also used as for inorganic qualitative analysis, but nowadays there is no available in the lab due to some license issues. So phosphorus is used in matches, fireworks, and fertilizer. Likewise, also nitrogen is also used as fertilizers, and so many oxides can be prepared by the nitrogen. And arsenic is toxic. It has been used as a poison and as a rodenticide. Antimony, rodenticide means a pesticide used to kill the rodents. Antimony finds use in alloys. Bismuth is used in medications, paint, and as a catalyst. Only a few atoms of MOSCOVIUM have ever been made, and they are only used in scientific study. It is used to make nihonium, that is When 243 americium reacts with bombarded with 48 calcium and forming 288 MOSCOVIUM, immediately they undergo radioactive decay by the emission of alpha to form nihonium, another element known as nihonium. These are some uses of nitrogen family members. Here only a limited applications are mentioned here. Liquid nitrogen is one form of or liquid form of nitrogen. That is, liquid nitrogen, that is also known as LN2, is nitrogen in a liquid state at low temperature, that is minus 196 degrees Celsius. It is produced industrially by fractional distillation of liquid air. It is colorless, low viscosity liquid that is widely used as a coolant. Liquid nitrogen, which has a boiling point of minus 196 degrees Celsius, is used for a variety of things such as coolant for computers, in medicine to remove unwanted skin, warts and precancerous cells, and in cryogenics, where the scientists study the effect of very cold temperature on materials. It has also become increasingly common at top restaurants as a method for instantly freezing food and drinks or creating an impressive cloud of vapor or fog when exposed to air. It is also used to make ice creams. For laboratory personnel in particular, there is also the risk of asphyxiation if liquid nitrogen, which is colorless, odorless and tasteless, is used or spilled in a confined space. Lab worker James Graham died from asphyxiation in 1999 because in the large amount of liquid nitrogen that will deprived of oxygen, that will cause unconsciousness and finally lead to death. So it is leading asphyxiation, so proper care should be taken in the lab if we are using, or in the restaurants also. Liquid nitrogen also a large expansion ratio on evaporation. 1 liter of liquid nitrogen can result in 700 liters of gas. From only 1 liter, a 700 liters of gas, a huge amount. So only a relatively small volume of liquid nitrogen has to evaporate within a room to result in an oxygen deficient atmosphere, that is causing asphyxiation. Pressure can build up in a sealed container due to the boil of nitrogen gas, so insulated vacuum jacketed pressure containers are used to store it. When it comes to using liquid nitrogen in cooking, Professor Barham says it is fine so long as safety measures are taken, otherwise creating an asphyxiation and leading to death. Electronic configuration. The valence shell electronic configuration of group 15 element is Ns2Np3, that is for nitrogen. Its electronic configuration is helium 2s2 2p3. Phosphorus atomic number is 15 and its electronic configuration is neon 3s2 3p3. Arsenic 33, argon 3d10 4s2 4p3. Antimony 51, krypton 4d10 5s2 5p3. Bismuth 83, xenon 4f14 5d10 6s2 6p3. The group number is same, that is 15, group 15 elements, and the periods ranging from 2 to 6. Here we can see the outer electronic configuration is 2s2 2p3 for nitrogen, 3s2 3p3 for phosphorus, 4s2 4p3 for arsenic, 5s2 5p3 for antimony, bismuth, 6s2 6p3. And we can, in the general valence shell electronic configuration of group 15 element is Ns2 Np3. This configuration with the extra stability, and this will lead to its physical and chemical characteristics of these particular elements. Atomic size of the nitrogen family members, that is nitrogen 70 picometer, for phosphorus 110 picometer, arsenic 121 picometer, antimony 141 picometer, and bismuth 148 picometer. That is, the atomic radius increases down the group with increase in atomic number of the elements. This is because one extra shell of electrons is added in each step. That is, atomic size increases from nitrogen to phosphorus, a significant increase or a considerably increase from the nitrogen to phosphorus, and there is a small increase from phosphorus to bismuth, and from phosphorus to bismuth there is only a considerable increase. This is due to the fact that the shielding effect of the N-1 S2 P6 electrons of phosphorus is large. The shielding effect of the N-1 D10 electrons of arsenic as well as antimony, and the N-2 F14 N-1 D10 electrons in the bismuth is poor. Here the shielding effect is poor, but when compared to nitrogen and phosphorus, phosphorus' shielding effect is large, and so the size increases here large, and here is only a small difference. The increased nuclear charge is more or felt on the arsenic, antimony, and bismuth, and increase in atomic size is less significant. That is why the size so much increases with the atomic number, not so much increasing with the atomic number. Ionization energy of the group 15 elements, that is nitrogen, shows ionization energy 1403 kilojoule per mole, and for phosphorus 1012 kilojoule per mole, and for arsenic 947 kilojoule per mole, and for antimony 834 kilojoule per mole, for bismuth 703 kilojoule per mole. The ionization energy decreases down the group to the gradual increase in atomic size. This is due to the highly stable half-filled configuration of p orbitals. That is, we know the general configuration of nitrogen family members is, outer electronic configuration is ns2 np3. np3 means the half-filled configuration, that is highly stable. Here one electron, and one electron, so it is in the half-filled, that is highly stable valence electron configuration. The sharp decrease in ionization energy from nitrogen to phosphorus is due to increase in, first case is increase in atomic size increases, that is from 70 to 110 picometer, and screening effect of S and P electrons in the case of phosphorus also increases. Two factors that cause decreasing ionization energy from nitrogen to phosphorus, that is atomic size is higher and shielding effect is also higher for phosphorus. The poor shielding effect of the arsenic, antimony, and bismuth decreases its ionization energy. Electronegativity. We can see from the table that the nitrogen is 3, phosphorus with 2.1, arsenic 2, and antimony and bismuth for 1.9. That is, the electronegativity decreases down the group. That is, nitrogen is the most electronegative element among the group 15 elements. Its value is 3. The electronegativity value decreases from nitrogen to bismuth, and large decreases from nitrogen to phosphorus. This is due to the increase in atomic size, that is here for nitrogen 70 picometer and for phosphorus it is about 110 picometer, and only small decrease from phosphorus to bismuth. This is due to increase in atomic size and also the poor shielding effect of the elements. Metallic character or electropositive character of group 15 elements, that is nitrogen, phosphorus, arsenic, antimony and bismuth. The electropositive character increases from nitrogen to bismuth due to the decrease in ionization energy from nitrogen to bismuth, and electronegativity value also decreases from nitrogen to bismuth. These two factors increases the metallic character from top to bottom of the group. That is, nitrogen and phosphorus act as non-metals, arsenic, antimony act as metalloids, and bismuth is a metal. Here nitrogen is exists in the gaseous state and other elements are present in the solid state. The metallic character, most metallic character in the nitrogen family is bismuth, and the least one is nitrogen. Metalloids are arsenic and antimony. Oxidation states. Nitrogen exhibits several oxidation states, mainly -3 to +5. Nitrogen exhibits a variety of oxidation states due to its small size, high electronegativity and strong tendency to form p-pi bonds. Valence electronic configuration of group 15 elements that we know, NS2, NP3, and the common oxidation states given by the group 15 elements is -3, +3 and +5. First we are discussing the negative oxidation states. When nitrogen reacts with highly electropositive metals to form nitrides, and nitrogen shows -3 oxidation state in these compounds. Here nitrogen with -3 and magnesium with +2 oxidation state. Same with the calcium nitride, +2 with the calcium and -3 with the nitrogen. These are ionic compounds. The other elements of the group also show -3 oxidation states in with the alkali and alkaline metals or with the transition metal. In this, calcium forms and phosphorus with the -3, calcium with the +2 and arsenic with the -3. Here sodium with +1 and antimony with the -3 and zinc with +2, and for bismuth -3, magnesium with +2. So these are but covalent compounds. Here magnesium nitride, calcium nitride as ionic compounds, but calcium phosphide, sodium arsenide, zinc antimonide and magnesium bismuthide are covalent compounds. In these compounds, both the group 15 elements shows -3 oxidation states. Nitrogen shows negative oxidation states of -3, -2 and -1 in covalent compounds, and tendency to exhibit -3 oxidation state decreases down the group due to the increase in size and metallic character. Among nitrogen shows -3 we can see in the covalent compounds and -2 in hydrazine, that is N2H4, N2 hydrazine, N2H4. Hydrogen we know +1 is the oxidation state, and here nitrogen with the -2, and for -1 in the case of hydroxylamine or hydroxylamine, that is OH NH2. In this particular compound, nitrogen is with a -1 oxidation state. Here nitrogen -1, hydrogen +1, oxygen -2 and hydrogen +1. These are covalent compounds. Tendency to exhibit -3 oxidation state decreases down the group due to the increase in size and metallic character. Now we are discussing the positive oxidation states of group 15 elements. All the group 15 elements show the positive oxidation states of +3 and +5. The stability of the +5 oxidation state decreases down the group and that of the +3 state increases down the group. This can be explained on the basis of inert pair effect. In the case of heavier elements, due to the poor shielding effect of the intervening d and f electrons, f orbital electrons, the effective nuclear charge holds the two ns electrons tightly and thereby restricts their participation in bonding. Thus, in the heavier elements of the group 15, there is an increasing reluctance for the ns pair to participate in bonding. This is called the inert pair effect and leads to cases where only the p electrons are involved in bonding, that is, only 3 electrons are involved in bonding. The heavier elements exhibit +5 oxidation state decreases and that of +3 state increases down the group. Bismuth 5 has a strong tendency to undergo reduction to the +3 oxidation state. Therefore, bismuth 5 is act as a strong oxidizing agent. It selfly reduces to Bi3 state. Nitrogen exhibits positive oxidation states from +1 to +5. That means for +1 we know in nitrous oxide N2O, here oxygen is in the -2 oxidation state, nitrogen is in the +1 oxidation state. That we can also say in the case of H2N2O2. And nitrogen also exhibit +2 oxidation state in nitric oxides. NO, oxygen with the -2 and nitrogen with the +2 oxidation state. And in the case of +3 oxidation state, we can see it in nitrogen trifluoride NF3 . We know fluorine is the most electronegative element, so it shows only negative oxidation state -1. So nitrogen with the +3 oxidation state, and +4 in the case of nitrogen dioxide NO2. Here oxygen with the -2, nitrogen with the +4. And in the case of +5 oxidation state, we can see nitrogen is in the +5 oxidation state of in nitric acid HNO3. Here oxygen with the -2, hydrogen with the +1. So nitrogen is in the +5 oxidation state. So nitrogen exhibits positive oxidation states from +1 to +5. And phosphorus can also shows +1 oxidation state in H3PO2. That is, it's a oxo acid of phosphorus. Oxygen with the -2, hydrogen with the +1. So -4 +3. Here phosphorus show +1 oxidation state. and plus 3 for phosphorus acid H3 PO3 oxygen shows minus 2, hydrogen shows plus 1, so phosphorus show plus 3 oxidation state, and plus 4 with the H4P2O6 diphosphoric acid with the phosphorus is in the plus 4 oxidation state, and plus 5 oxidation state in phosphoric acid, that is H3PO4. Here plus 5 oxidation state. So phosphorus can also shows plus 1, plus 3, plus 4 and plus 5 oxidation state. And arsenic, antimony, bismuth shows plus 3 oxidation state in its compounds. These are the positive oxidation states exhibited by the group 15 elements. And nitrogen shows a variety of oxidation states due to its allotropy. Allotropy or allotropism, meaning other, meaning manner, is the property of the some chemical elements to exist in two or more different forms in the same physical state, known as allotropes of the elements that we know. And the group 15 elements show allotropy. Beta nitrogen. Nitrogen is the first element that shows an allotropic form of beta nitrogen. At atmospheric pressure, molecular nitrogen condenses at 77 Kelvin, that is, it converted to liquid nitrogen, and freezes to solid form at 63 Kelvin. This solid form, beta hexagonal close packed crystal allotropic form, that is known as beta nitrogen. It is an hexagonal form. Another one is alpha nitrogen. Below 35.4 Kelvin, that is minus 237.6 degrees Celsius, nitrogen assumes the cubic crystal allotropic form called alpha nitrogen. Solid nitrogen has many crystalline modifications. It forms a significant dynamic surface to coverage on Pluto and outer moons of the solar system such as Triton. Another one is black nitrogen. In early 2020, researchers at the University of Beirut found a new allotrope, the so-called black nitrogen. It has the structure similar to that of black phosphorus. It is created in a diamond and will at a pressure of 140 gigapascal, that is 1.4 million bars, and a temperature of 4000 degrees Celsius, and is only stable in such extreme conditions. It is actually transparent, and in that experiment it was heated by a strong laser. Phosphorus. Allotropic forms of phosphorus are, first one is white phosphorus, exists in two crystalline forms, that is alpha and beta. At room temperature, the alpha form is stable, which is more common, and it has a cubic crystal structure. And at 195.2 Kelvin, it transforms into beta form, which has hexagonal crystal structure. These forms differ in terms of the relative orientations of the constituent P4 tetrahedra. White phosphorus is least stable and the most reactive and the most volatile and the least dense and the most toxic of the allotropes. White phosphorus gradually changes to red phosphorus. This transformation is accelerated by the presence of light and heat. When exposed to oxygen, white phosphorus glows in the dark with a very faint tinge of green and blue. It is highly flammable and pyrophoric, that means self-igniting upon contact with air. The odor of combustion of this form has a characteristic garlic smell, and samples are commonly coated with white phosphorus pentoxide which consists of P4 or 10 tetrahedra with oxygen inserted between the phosphorus atoms and at their vertices. White phosphorus is insoluble in water but soluble in carbon disulfide. So the least stable and the most reactive, most volatile allotrope is white phosphorus, which is exists in two crystalline forms, alpha form and beta form. Red phosphorus is polymeric in structure. Red phosphorus may be formed by heating white phosphorus to 250 degrees Celsius or by exposing white phosphorus to sunlight. Phosphorus after this treatment is amorphous. Upon further heating, this material crystallizes. Red phosphorus is actually an intermediate phase between the white and violet phosphorus. After prolonged heating or storage, the color darkens and the resulting product is more stable and does not spontaneously ignite in air. Violet phosphorus is a form of phosphorus that can be produced by day-long annealing of red phosphorus above 550 degrees Celsius. In 1865, Hittorf discovered that when phosphorus was recrystallized from molten lead, therefore this form of violet phosphorus is sometimes known as Hittorf's phosphorus or alpha metallic phosphorus. Black phosphorus is the least reactive allotrope and it is highly stable form below 550 degrees Celsius. It is also known as beta metallic form. Violet phosphorus known as alpha metallic phosphorus. Black phosphorus is the stable one and it is known as beta metallic phosphorus. It is obtained by heating white phosphorus under high pressures. Scarlet phosphorus, another allotrope of phosphorus, is obtained by allowing solution of white phosphorus in carbon disulfide to evaporate in sunlight. Allotropes of arsenic. The three most common arsenic allotropes are grey, yellow and black arsenic, with grey being the most common. Grey arsenic adopts a double-layered structure consisting of many interlocked ruffled six-membered rings. Because of the weak bonding between the layers, grey arsenic is brittle. Grey arsenic is a semi-metal but becomes semiconductor with a band gap of 1.2 to 1.4 electron volt if amorphized. Grey arsenic is also the most stable form of allotrope. Yellow arsenic is a soft and waxy and is somewhat similar to tetraphosphorus. This unstable allotrope, being molecular, is the most volatile, least dense and most toxic one. Black arsenic is similar in structure to black phosphorus. It is glassy and brittle. It is also poor electrical conductor. So there are three forms of allotropes for arsenic, that is grey, yellow and black. Antimony. Allotropes of antimony. 4 allotropes of antimony are known: a stable metallic form and 3 metastable forms, that is explosive, black and yellow. Elemental antimony is a brittle, silvery white, shiny metalloid. A rare explosive form of antimony can be formed from the electrolysis of antimony trichloride. When scratched with a sharp implement, an exothermic reaction occurs and white fumes are given off as metallic antimony is formed. That is the most stable one. When rubbed with a pestle in a mortar, a strong detonation occurs. Next one is black antimony is formed upon rapid cooling of antimony vapor. It has the same crystal structure as the red phosphorus and black arsenic. At 100 degrees Celsius, it gradually transforms into the stable form. The yellow allotrope of antimony is the most unstable one. Above the temperature, that is a low temperature, and in ambient light, this metastable allotrope transforms into the most stable black allotrope. So there are 4 allotropes of antimony. One is metallic antimony and 3 metastable forms, that is black antimony, yellow antimony and explosive antimony. Atomicity. Nitrogen exists as a diatomic gaseous molecule, that is N2. Phosphorus exists as a tetraatomic solid molecule, that is P4. This is due to the significant repulsions from the non-bonding electrons of the penultimate shells of phosphorus. Their atoms cannot approach each other sufficiently closely to cause effective p-pi bonds sideways by the sideways orbital overlaps. They form giant lattices, and bonding in these lattices gradually change from covalent to metallic on moving down the group. White phosphorus is a white, translucent, waxy solid with a garlic smell. It consists of discrete tetrahedral P4 molecules. All the phosphorus bond angle is 60 degree. It is least stable and more reactive form of phosphorus under normal conditions due to the angular strain in the P4 molecule. The reactivity of white phosphorus is attributed largely to this strained structure. It readily catches fire in air to give dense white fumes of phosphorus pentoxide, that is P4 or 10. It does not react with water and hence can be safely stored under water. Red phosphorus is polymeric and consists of chains of P4 tetrahedra linked together, that we can see in this picture. Red phosphorus does not ignite readily in air. Violet phosphorus and stable black phosphorus, that is alpha and beta forms, have polymeric structures of high molecular mass. Arsenic and antimony vapors presumably contain As4 and SbF4 molecules respectively. They have closely packed layered structure having forces intermediates between those of covalent and metallic bonding. Here we can see from the table, nitrogen shows atomicity 2, phosphorus 4, arsenic 4, antimony 4, bismuth forms a metallic bond, and MOSCOVIUM under study. Thank you for your attention.